Hello and welcome to MyScience Tutorials. In today's video, we are going to be talking about the introduction to wave motion and progressive wave equation. Before we begin, if you are new to MyScience Tutorials, make sure you consider subscribing and pressing that notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. So we want to start by looking at what a wave is. So a wave is a disturbance which travels through a medium that enables the transfer of energy from its source to another point without the transfer of the particles in the medium. So as we can see in this illustration over here, we can see that the center of disturbance is where we have the wave being generated, and we can see that the energy is being transferred to other part of the medium. So this is how a wave looks like, or when it's generated. And this is a graph that shows how the wave is being generated. So it goes in a form of semicircles, up and down, and it forms the wave. Now if we are looking at it from the top, this is how it will appear. So we have the wave being generated, and then the center over here is where the source or the disturbance is, and then the energy as a result of that disturbance is being transferred to other parts of the medium. Now, the disturbance that conveys the energy from one point to another without the transport of the matter itself is called progressive wave. So when we have a disturbance that generates a wave, and in this generation of the wave, we don't have the matter being moving, okay, but just the energy being conveyed from one point to the other, we call that type of wave a progressive wave. We call that type of wave a progressive wave. Now, waves are broadly grouped into two. We have the mechanical waves and then the electromagnetic waves. So we want to look at what this type of waves are. So a mechanical wave, these are the types of waves that requires a material medium for the transmission of energy from one source to the other. For instance, we have a good example is water waves, sound wave, and seismic waves. So we have water waves when we, let's say, drop a stone in a pond or a water body. We can see that the waves are being generated as shown in this diagram over here. So this center that we have over here, this can be what our source of what disturbance. So we get to realize when we drop a stone over here, so assuming we drop a stone over here, as the stone enters the water body, okay, waves will be generated and the energy will be transferred to other parts of the water body. Now, one thing we need to note is that as the wave is being generated, the energy it takes to spread out reduces as the distance increases. So at the waves at the source of impact will be greater than if you go to the edges, the energy at the edges. Now, another example is sound wave. So we normally use this sort of bars to represent sound waves. And then the seismic waves, we have the seismic waves when we have the movement of the earth parts. So for instance, if we have an earthquake or volcanic eruption, this causes some movement of certain parts of the earth, and this generates certain types of waves, and these types of waves are what we call the seismic waves. In all these three examples, you get to realize that the wave needs a medium to propagate the energy. That is, in water waves, water serves as a medium to transfer the energy. In sound wave, the air around you serves as your medium to propagate the sound to someone else. So let's look at electromagnetic waves. Okay, so these are the types of waves that do not require a material medium for their propagation. Thus, they travel in vacuum. So good examples are the gamma rays, the X-ray, the UV radiation, and an infrared radiation. Okay, so these are types of electromagnetic waves. They do not need any material medium. They travel in vacuum. All right. So let's have a look at a progressive wave in general. So we said progressive waves is generated, or they are generated when a disturbance conveys an energy from one point to the other without the transport of the matter itself. Now, depending on the direction of the particle vibration with respect to the direction of travel of the wave, we can distinguish between two types of progressive waves. So we have one, the transverse wave, and two, the longitudinal waves. Transverse waves. A wave is said to be a transverse wave if the direction of travel of the wave is perpendicular to the direction of vibration of the medium. So if we look at this diagram over here, okay, assuming this is our source of disturbance, okay, or we drop a small stone over here, and this, we are looking at this horizontal line as our water body, or our medium. Okay, we get to realize that as we drop the stone, this should be a downward arrow. As we drop the stone from top to down, this is vertical. Okay, but we see that the wave generated move in a horizontal manner. That is, this is the water body without the disturbance. Now, after the stone has been dropped into the water, or we've generated a disturbance, we can see that the wave goes up and down, and it continues in that way until it dissipates. So this movement, you can see that the movement of the wave is what? Is perpendicular to the direction of the source of the vibration or the source of disturbance. So this type of wave, we call it transverse wave, because the direction of the travel of the wave is perpendicular to the direction of the vibration or the source of the disturbance within the wave. Now, when we have a transverse wave, there are two parts that we need to take note of. You can see that when the wave travels up and down, the top over here, the highest point over here, is what we call the crest, or the top over here. This is what we call the crest. Okay, the downward displacement of the wave is what we call the trough. Okay, so the crest is the region of upward maximum displacement. Okay, so this upward maximum displacement is what we call the crest, and this downward maximum displacement is what we call a trough. Now let's look at what longitudinal waves are. So longitudinal waves occurs when the vibrations occur in the same direction as the direction of travel of the waves. They behave like spiral springs that has a series of what? Compressed regions and spaced out regions traveling along it. Okay, so longitudinal waves, these waves are generated when the source of vibration and then the source of movement of the wave are in the same direction. So we normally use these lines to represent what? A longitudinal wave. So as the name suggests, they are longitudinal. Okay, so the direction of the wave and then the source of disturbance also moves in the same direction. Now if we look at it, we can see that it is being described as being a spiral spring. So when you pull a spring, you get to realize there are some parts that are close to each other, okay, like this side over here, and there are other parts that are far away from each other, like this side. Okay, so the parts that are very close to each other in the longitudinal waves, we call them C, or the compression. Okay, it's denoted by C. And the parts that are further apart, we call them the rarefaction. Okay, so you can see that the parts that are further apart, we call them rarefaction. The parts that are very close to each other, we call them compression. Now let's have a look at the general representation of a wave. So generally, if you want to represent a wave, we use the the transverse way of showing a wave. Okay, so that is, we always assume the direction of the source of the impact to be what? Perpendicular to the movement of the wave. So this is how we generally represent a wave. On our vertical axis, we have the displacement or the source of impact. On our horizontal axis, we represent that with the time. Okay, so it's just a plot of what? Displacement against time. Now there are certain parts of this general representation that we need to know. If we look at this, let me do this. Okay, if we look at this, we can see that the highest distance over here traveled by the wave as it goes up and is about to come down, the highest distance over here is what we call the amplitude. So this is the amplitude. Okay, now if the wave starts here, okay, where it starts and then where it ends, okay, or if the wave makes a complete circle, because this is a semicircle, this is another semicircle. If you bring the two of them together, we form a complete circle. Okay, so the beginning of the wave to the end of the wave is what we call the wavelength. Or if we extend this wave, let me use that light blue color. So if we extend this wave like this, okay, the distance between the crest over here and then the crest over here, okay, the distance between two successive crests can also be described as what? The wavelength, or the distance between two successive troughs. So assuming we continue these waves in this direction, something like this, okay, so the distance between the trough over here and then the trough over here, from here to here, can also be what? Another wavelength. So the distance between two successive crests is a wavelength, the distance between two successive troughs is also a wavelength, and then the distance between what? The beginning of a wave and then when it makes one complete circle can also be called a wavelength. Now, the time it takes for the wave to make a complete circle is what we call the period. Okay, and then the number of complete waves that are being produced in a second is what we call the frequency. So let's look at all these terminologies in much more detail. So we have amplitude. So the amplitude, this is the maximum displacement of a particle from the mean position of rest. Okay, so the SI unit is in meters. So like I showed you earlier on, the upward displacement, okay, or the maximum displacement of the particle from the mean position as shown over here is what we are referring to as our amplitude. Now the period, this is the time taken for a wave to make a complete circle. So if you look at this is a semicircle, this is another semicircle, okay? So the time it took this wave to make this complete circle is what we are calling the period, and the SI unit is in what? Seconds. We have the frequency. This is the number of complete circles a wave undergoes in a second. So if a wave is able to undergo, let's say 10 complete circles in just a second, okay, it means the frequency of that wave is 10. If it's only able to undergo 2 complete circles or 2 complete revolutions before a second is reached, it means it has what? 2 hertz as its frequency. Now the wavelength, like I said earlier on, this is the distance between 2 successive crests or troughs, or it's the distance covered by a wave after one complete circle, like I explained. So the distance covered by a wave as it makes one complete circle is the wavelength, or the distance between 2 successive crests over here is also wavelength, or the distance between 2 successive troughs as shown at the bottom over here can also be defined as what? Wavelength. Now we come to look at what the velocity is. So velocity, this is the distance traveled by a wave in a second. Okay, it is often called the wave velocity or the wave speed. The SI unit is in meters per second. Alright, so now that we are familiar with some terminologies about wave, let's look at the relationship between these terminologies. So we want to look at the relationship between time, frequency, wavelength, and velocity. Now, if you look at the definition of frequency over here, we can say that this is the number of what? Complete cycles, okay, a wave undergoes in a second. Okay, so it means the frequency is inversely proportional to time, because if you look at time or the period, this is the time taken for a wave to make a complete circle. So the time taken to make a complete cycle, and then the frequency is the number of complete cycles made, okay, produced in a second. Okay, so the relationship between the frequency and then the period is the inverse proportionality. So the frequency is inversely proportional to the period, or the period, which is t, is inversely proportional to the frequency. That is the first relationship that we want to look at. So let's make that equation 1. Alright, the velocity, from the definition over here, we said what? This is the distance traveled by a wave in a second. So it means we are talking about the distance, okay, with respect to time. Now the distance in this wave motion is what we are saying is what? Our lambda, and then the time is t. Okay, so the SI unit is what? in seconds. This is t, time is t. The SI unit is in seconds. This one is in meters. So the SI unit over here is what? Meters per second. Okay. Anyway, so it means velocity is equal to what? The wavelength lambda over what? The time, which is what? T. Okay. But from the equation 1, okay, we said what? Time over here, time is equal to what? 1 over what? Frequency. Okay, so let's substitute this in place of this. So we have lambda over what? 1 over frequency. Now if we rearrange these, we are going to get velocity is equal to, if we bring 1 over f to the top to come and multiply lambda, it becomes what? Just the frequency. So we have this will be lambda multiplied by what? The frequency. So it means velocity is equal to what? F lambda. This is equation 2. So this is the relationship between velocity, frequency, and then the wavelength. Okay, they are directly proportional. All right. So let's go ahead. Let's now look at the progressive wave equation. Now we've already looked at what the graph looks like. Now we can see that there is a new arrow over here that we are representing with P. Now what is this P? Now if the wave move from, let's say, the left to right, so we are moving from our left to our right. So if the wave move from left to right, the particle at O, okay, the particle at O over here will be displaced first before the particle at P over here. So if the wave is being generated, we can say that the particle at O over here will be displaced first before any other particle at P will then be displaced later on. So if that happens, we therefore say that what? The particle at O lead the particle at P. So we say the particle at O, okay, lead, okay, the particle at P, or we can say the particle at P lag on O. Okay, so this is 1, this is particle at P lag on what? The particle at O. Okay, so the fact that the particle at P lag on particle of O, or the particle of O lead the particle at P, is by a phase angle, and that phase angle is what we have over here. Okay, so we represent that with this, and this is what we call our phase angle. Now the phase angle is given mathematically as what? 2 pi x over lambda. Okay, so this is the phase angle. So if the displacement of O, which we said will occur before the displacement of the particle at P, we therefore say what? That the particle at P lags on particle at O by the phase angle, or the particle at O lead the particle at P by this phase angle. Now the displacement of the particle at O, over here is given by the wave equation. Y is equal to what? A sine angular velocity multiplied by time. Okay, so this is the general equation for the particle at O. Now if the displacement of the particle at P, which lags on O, if you want to write the displacement of the particle at P, which lags on O, we write that as what? Y is equal to what? A sine, then into bracket angular velocity minus what? The phase angle that we are talking about. Because already we said the particle at O will move before the particle at P. So it therefore means we need to subtract something, or we need to subtract the phase angle from the displacement equation of the particle at O for us to be able to get the displacement equation of the particle at P. Now the angular velocity over here is given by what? 2 pi v on what? On lambda. So if we do the substitution of the angular velocity over here angular velocity over here, and then the phase angle over here, we now have a new equation that looks like this. So let me use this blue. So we now have a new equation that looks like this. So if we do the substitution for this equation, we now have y is equal to a sine, then into bracket, we said the angular velocity is what? 2 pi v over lambda, then multiplied by the time, minus the phase angle, which we said is what? 2 pi x over what? Over lambda. Alright, but we know that our velocity is equal to what? F lambda. So it means if we make frequency the subject, okay, if we make frequency the subject over here, we are going to get frequency is equal to what? Velocity over what? Lambda. So which means this part of the equation, let me use this color. The velocity with respect to the lambda over here, in place of everything over here, we can represent that by what? The function f, or the frequency. So if we do that, the whole equation becomes what? Y is equal to what? A sine into bracket 2 pi f t minus what? 2 pi x over what? Over lambda. So this equation is what we call the progressive wave equation, okay, where the y over here, okay, is the displacement of any particle from the origin. Now the x over here is the distance of the particle from the origin. So as we can see, if this is the origin, this is the s that we are talking about. So it's the distance of the particle from the origin. Now the v that we have, okay, from this side is the velocity of the wave, we know. The a over here is the amplitude of the wave. The f over here is the frequency of the vibrating particle, and then the pi is definitely a constant, and then the t is the period of the wave. All right, so now that we are done with this, let's move on. But before we go on, we can see that in this diagram we said what? The wave was moving from what? The left to the right, okay, and that is how come we are subtracting the phase angle from that of the general wave from the origin. But what if we have the wave moving from the right, okay, to the left? Okay, so if that happens, the only thing that changes in this progressive wave equation is that we have the equation, instead of having negative over here, it becomes what? Positive, because we need to add the phase angle. So we have from left to right, okay, or that is in the opposite direction, we have the equation y is equal to a sine into bracket 2 pi ft plus what? 2 pi x on what? Lambda, or wavelength. All right, so with this being the case, let's have a look at an example. So we have a wave profile is represented by y is equal to what? A sine into bracket 2000 pi t minus pi x on what? 17. We have to calculate for its I wavelength, II velocity, III frequency, and IV the period. So let's go ahead and look at how we solve a problem like this. So we have, first of all, we start by, let's write the general wave equation. So the general wave equation we know is y is equal to what? A sine into bracket 2 pi ft minus what? 2 pi x on what? All on this is just one, all on wavelength, or lambda. All right, so if we rewrite the general wave equation that we have been given in the question, we have y is equal to what? A sine into bracket 2000 pi t minus what? Pi x over what? 17. All right, so it means if we compare these two equations, we can see that we have a sine here, a sine over here. Now if we look at this part and this part, we can see that there's a difference. Okay, so we can equate these two sides of the general wave equation. So we have what, 2 pi ft should be equal to what, 2000 pi t. Okay, so from here we can cancel out the pi's that we have. We can cancel the pi with this, we can cancel the time with this. So from here we have 2 multiplied by the frequency is equal to what, just 2000. So we divide both sides by 2, we get our frequency to be what, 1000 hertz. Okay, so straight away from here we know our frequency is going to be what, 1000 hertz. Now we've been asked to find the period. We have the period in the question, but we know period, okay, period is what, 1 over period, which is t, is equal to 1 over frequency. Now we already calculated for the frequency, so it means 1 over what, 1000, okay, is going to give us our period, okay, and that is equal to what, 1 times 10 raised to the power negative 3 seconds. All right, now let's move on. If we look at this, we also need to find wavelength and the velocity. So what do? Let's equate these two equations again. So we have a 2 pi ft is equal to what, this 2000 pi t over here. Now remember we did some substitution where we substituted frequency in place of velocity and wavelength. Okay, so we said what, velocity is equal to what, f lambda. Okay, and if we make frequency the subject over here, we get what, velocity on wavelength. So it means in place of frequency over here, we can substitute this over here. So we have 2 pi v on lambda t, okay, is equal to what, 2000 pi t. Okay, so it means the pi can cancel the pi, the time can cancel the time over here. So we have 2v on pi is equal to what, 2000. Okay, so let's make this equation 1. All right, let's have a look at another aspect. If we look at this side and this side, we can see there is a difference, so we can equate those two. So we have 2 pi x on lambda is equal to what, pi x on what, 17. So if we cancel out these two over here, we're going to have 2 multiplied by 17, that is going to give me 34, is equal to lambda multiplied by, here will become 1, it becomes what, lambda. So it means our wavelength is what, 34. So it means lambda is equal to what, 34 meters. Okay, but now that we have lambda, we have frequency, we can now calculate for our velocity. Okay, we know velocity is equal to what, f lambda. Okay, so from here we know that our velocity, okay, from here we know our velocity will be equal to the lambda, the frequency, which is 1000. So we have 1000 here multiplied by the lambda, which is 34. So we have the velocity to be what, 34,000 meters per second. Or from the equation 1 that we have over here, it means 2v is 2v over the lambda, which is 34, is equal to what, 2000. Okay, so if we cross multiply, we have 2v is equal to what, 34 multiplied by what, 2000. Okay, so if we divide both sides by 2, we get to rather 2 go here 1, it will go here 1000. If we use the 1000 to multiply the 34, we get our velocity to be what, 34,000 meters per second. So therefore we can conclude that our wavelength, okay, is what, 34 meters. Our velocity is what, 34,000 meters per second. Our frequency, our frequency is what, 1000 hertz. And IV, our period is what, times 10 raised to the power negative 3 seconds. So this is the answer for this example. So let's go ahead. So example number 2, we have a plane progressive wave is represented by y is equal to what? Y is equal to 0.1 sine 200 pi t minus what? 2 minus 20 pi x on 17, where y is the displacement in millimeters, t is time in second, s is the distance from a fixed origin o in meters. So we have to calculate for the frequency of the wave, the wavelength, the speed, the period, then the phase difference in radians between the point 0.25 meters from O and the point 1.10 meters from O. So let's have a look at the solution. So as usual, the first thing we do is what? We write the progressive wave equation because we need to compare. So we have y is equal to a sine into bracket 2 pi ft minus what? 2 pi x on what? On lambda. But the equation we've been given in the question is what? A is equal to what? 0.1 sine into bracket 200 pi t minus what? 20 pi x on what? 17. Alright, so the first question is telling us to find frequency. So for frequency, we know we have frequency over here, we don't have f over here, so we can equate these two. So we have 2 pi ft is equal to what? 200 pi t. So the pi t will cancel out, so we have 2f is equal to what? 200. So it means our frequency is equal to what? 100 hertz. Straight away from there, we know our frequency it's 100 hertz. So let's look at the II. So we have to calculate the wavelength. Okay, so the wavelength over there. So calculate the wavelength. That is the second aspect. So the wavelength, we can see wavelength over here. So we can compare these two. So we have 2 pi x on lambda should be equal to what? 20 pi x on what? On 17. So the pi x can cancel each other out. So it means we have the 2 here will now multiply the 17, which will now give me 34 to be equal to the wavelength over here will multiply the 20, and that gives me what? 20 pi. So we divide 20 lambda. So we divide both sides by 20. We get our lambda to be equal to what? 1.7 meters if we divide 34 by 20. Now the next thing we want to look at is the speed, the speed or the velocity. So we know velocity is what? F lambda. So straight away we know we've already found our frequency, we have our lambda or the wavelength, so we can find velocity easily just by multiplying what? 100 by 1.7. So if we do that, multiply 100 by 1.7, we are going to get what? 170 meters per second. Okay, right, let's look at IV. So IV, we have to find the period. As easy as ABC, we know period or the time is equal to what? 1 over frequency. So it means our period is what? 1 over the frequency is what? 100. So it means our period over here, our period is equal to what? 0.01 second. Alright. Now, the last aspect of the question is telling us to find the phase difference in radians between a point 0.2 meters from the origin and a point 1.1 meter from the origin. Now, like I said earlier on, that is this is IV. Like I said, phase angle is equal to what? 2 pi x over what? Over lambda. Now we have our lambda, which is 1.7. We know pi is a constant. We have to find the phase angle. So the only thing left is what? The x over here, which is what? The distance. Now we have to find it between two distances. So if we subtract the highest from the lowest, if we subtract the lowest from the highest of these 2 points, we get the value of x. Then we can substitute that, and then we find our phase angle. So if we do the subtraction, it means our x will be equal to what? The highest over here is 1.1. okay, meters. Then we subtract the 0.25 meters from that. We get our x to be equal to what? 0.85 meters. So now that we have the value of x, it means our phase angle is equal to what? 2 pi into bracket 0.85 on what? Our lambda, which is what? 1.7. Our phase angle is equal to, if we multiply 2 by 0.85, you're going to get 1.7 pi over what? 1.7. So this cancel out, so it means our phase angle is equal to what? Pi radians as our answer for this question. So our frequency is 100 hertz, our wavelength is 1.7 meters, our velocity is 170 meters per second, our period is 0.01 second, and then our phase angle between these 2 points, that's 0.25 meters from the origin and 0.1.10 from the origin, is what? Pi radians. Now let's have a look at one final example. Alright, so a progressive wave is represented by the equation y is equal to 10 sine 4 pi into bracket 15t plus what? X. So we have to calculate the amplitude, the wavelength, the velocity, and the frequency. So as easy as a piece of cake. So let's write down the solution. So we have the equation, the progressive wave equation. We know is a sine into bracket 2 pi ft minus 2 pi x on what? On lambda. So the one we are given is what? Y is equal to what? 10 sine into, 10 sine, let me erase this. Then sine 4 pi into bracket 15t plus what? X. Now if we look at this, we get to realize this is not exactly in the form as the general progressive wave equation, because we have the pi outside, so we need to expand this. So if we do the expansion, we are going to get 10 sine, then we multiply 4 pi by this, we are going to get what? 4 multiplied by 15, that is going to give us 60 pi t. Okay, so we have 60 pi t plus 4 multiplied by this, we are going to have what? 4 pi x. So this now becomes what? Our equation. That is, if we expand what we have over here. So straight away, let's look at what the amplitude is. So if we compare this equation, let's see equation 1 and equation 2. If we compare these two equations, the amplitude is the A over here. So if we compare the two, the A is equal to what? 10 meters straight away. Now the II, we have to find what? The wavelength, which is what? Lambda. Okay. If we look at the two equations, we have wavelength over here. So we compare these two sides of the equation. This is plus, so it means this also has to be plus, because that means the wave is moving from what? The right to the left. So if we compare these two guys, we have 2 pi x on lambda to be equal to what? 4 pi x. Okay, so this should be over 1. So these two guys will cancel these two guys. So we have this will not multiply this, so we have 4 pi is equal to 4 lambda. 4 lambda is equal to the 2 multiplied the 1 is equal to 2. So we divide both sides by 4. We have our wavelength to be what? 0.5 meters. Alright, so now that we are done with that, we now have to find what? Velocity. So I velocity. Now we can see that before we are, velocity is what? F lambda. Okay, before we find the velocity, we need to find the frequency, because we don't know the frequency, and we can find the frequency from here. So if we compare, let's jump to IV first. So if we compare, we have what? 60 pi t here should be equal to what? 2 pi f t over here. So the pi t's will cancel out, so we have 60 to be equal to what? 2f. We divide both sides by 2, we get our frequency to be what? 30 hertz. And now that we have the frequency to be 30, it just means that our velocity now is 30 multiplied by what? 0.5. and that will give us what? 15 meters per second as our velocity. So thank you guys so much for watching, and I will see you in the next video. Bye bye.